Everyone, I am Yuan Fang with metric number 203127, and today I am going to talk about static. And here I am going to talk about the general principle of static first. For static, we have basic quantities. Here is the example: length, time, mass, and force. And meter, second, gram, and newton are the units for the length, time, mass, and force respectively. Also, there is Newton's three laws of motion. The first law is a particle originally at rest or moving in a straight line with constant velocity tends to remain in this state provided the particle is not subjected to an unbalanced force. And the second law of motion is a particle act upon by an unbalanced force F experience an acceleration A that has the same direction as the force and a magnitude that is directly proportional to the force. And finally, the third law of motion is the mutual forces of action and reaction between two particles are equal, opposite, and collinear. There is also the Newton's law of gravitational attraction, and the formula is F equals to G m1 m2 over r squared. As the F is force of gravitation between the two particles, G is the universal constant of gravitation, and according to the experimental evidence, G is 66.73 power of negative times 10 power of negative 12 meter cube kg dot second square. And m1, m2 is the mass of each of the two particles, while r is the distance between the two particles. Also, there is SI units and US customary. So, SI unit is the international system of units where the length use m, time use s, mass use kg, and force use newton. While the US customary, the length using foot, time using second, mass using slug, and force using pound. Here we are entering the second chapter, force vectors. What is force vectors? A scalar is a positive or negative number, mass and temperature, such as mass and temperature. A vector has a magnitude and direction, where the arrowhead represents the sense of the vector. On the right side is the vector, and the multiplication of division of a vector by a scalar will change only the magnitude of the vector. If the scalar is negative, the sense of the vector will change so that it acts in the opposite sense. If the vectors are collinear, the resultant is simply the algebraic or scalar addition. We can see on the right side, the R is equal to A plus B when the values are collinear. So there is parallelogram law. Two forces act according to the parallelogram law. The components form the size of the parallelogram, and the resultant is the diagonal. To find the components of a force along any two axes, extend lines from the head of the force parallel to the axis to form the components. Here, the right side, this is the resultant vector, and this is the parallelogram. So to obtain the components of the resultant, show how the forces acted by tip to tail using the triangle rule, and then use the law of cosine and the law of sine to calculate their values. To find the resultant force, we can use this formula, which is square root f1 square plus f2 square minus 2 f1 f2 cos theta. And this is the law of cosine. We can use this to find the force in the vector. The rectangular components, two dimensions. Vector fx and vector fy are rectangular components of f, which is shown in here. The resultant force is determined from the algebraic sum of its components. Frx equal to total fx, Fry equals to total fy, and Fr equals to square root Fr(x) squared plus Fr(y) squared. To find the angle, we can also use this formula right here. And the Cartesian vectors, the unit vector u has a length of 1, no units, and is point in the direction of the vector f, as this example shows. And a force can be resolved into Cartesian component along the xyz axis, so that F equals to Fxi plus Fyj plus Fzk. The magnitude of F is determined from the positive square root of the sum of the squares of its component. This is the formula for this magnitude of F. The coordinate direction angles alpha, beta, and gamma are determined by formulating a unit vector in the direction of F. The x, y, z components of U represent cos alpha, cos beta, cos gamma. And this is the formula of this. So from this example, we can find the U in each the U of the F by using this formula. The coordinate direction angles are related so that only two of the three angles are independent of one another. To find the resultant of a concurrent forces system, express its force as a Cartesian vector and add the ijk component of all the forces in the system, which is shown in here. To find the resultant of the concurrent force system, we can use the formula of this. The position at force vector. A position vector locates one point in space relative to another. The easiest way to formulate the components of a position vector is to determine the distance and direction that one must travel along the xyz direction, going from tail to the head of the vector. This is the formula for R. And how to find R, we can use the formula of this to find the Cartesian vector of ijk, of R, sorry. So, if the line of action of a force passes through point A and B, then the force acts in the same direction as the position vector R, which is defined by the unit vector U. The force can be expressed as a Cartesian vector. If the line, here is the example, show that the line of action of force passes through point A and B, then the force acts in the same direction as the position vector R. Then you can use the formula of this to find F. We come to dot product. The dot product between two vectors A and B use a scalar. If A and B are expressed in Cartesian vector form, then the dot product is the sum of the products of their xyz component. The dot product can be used to determine the angle between A and B. So A dot B equals to AB cos theta. We can see from this example AB cos theta, and how to get the A dot B, we can use this formula AX BX plus AY BY plus AZ BZ, and the theta we can find using this formula. The dot product is also used to determine the projected component of a vector A onto an axis AA defined by its unit vector U. So we can find vector A using this formula, and from this example we also can see that if you want to find the A vector, you can A vector of U, you can A cos theta times with UA. And we have come to the equilibrium of a particle. When a particle is at rest or move with constant velocity, it is in equilibrium. This requires that all the forces acting on the particle form a zero resultant force. Means that the resultant force is equal to zero. In order to account for all the forces that act on a particle, it is necessary to draw its free body diagram. This diagram is an outline shape of the particle that shows all the force listed with their known or unknown magnitudes and direction. If the problem involved a linearly elastic spring, then the or compression x of the spring can be related to the force applied to it. So the formula is F equal to Kx. The tensile force developed in a continuous cable that pass over a frictional pulley must have a constant magnitude throughout the cable to keep the cable in equilibrium. The two-scalar equation of force equilibrium can be applied with reference to an established xy coordinate system. The total force of x and total force of y are equal to 0. If the three-dimensional geometry is difficult to visualize, then the equilibrium equation should be applied using a Cartesian vector analysis. This requires first expressing each force on the free body diagram as a Cartesian vector. When the forces are summed and set equal to 0, then the I, J, and K component are also 0. So to find the total force of F, we can assume that total Fx, total Fy, and total Fz are 0. So you can find F. And we come to the equilibrium of a rigid body. A body in equilibrium is at rest and can translate with constant velocity is equilibrium. As we said just now, total F is equal to 0. Before analyzing the equilibrium of a body, it is first necessary to draw its free body diagram. This is an outline shape of body which show all the forces and couple moments that act on it. Couple moments can be placed anywhere on a free body diagram since they are free vectors. Forces can act at any point along their line of action since they are sliding vectors. Angle used to resolve forces and dimension used to take moments of the forces should also be shown on the free body diagram. Some common types of support and their reaction are shown below in 2 dimensions. So we can see that this is the free body diagram, and we have to list down a lot of things on the free body diagram in order to know that what we are doing. Remember that a support will exert a force on the body in a particular direction if it prevents translation of a body in that direction. It will exert a couple moment on the body if it prevents rotation. The three-scalar equation of equilibrium can be applied when solving problems in 2 dimensions, since the geometry is easy to visualize. So we assume that when in equilibrium, the total Fx and total Fy are equal to 0. When the equation are equal to 0, we can easily find the missing number or the unknown number. For the most direct solution, try to sum forces along an axis that will eliminate as many unknown forces as possible. Some moments about a point A that passes through the line of action of as many unknown forces as possible. So the total Fx is equal to 0 and the total MA is equal to 0. There is equation here to find the forces of A and B. Some common types of supports and their reaction are shown here in 3 dimensions. There is examples such as roller, ball and socket, fixed support. So these are the free body diagram of this example. And in 3 dimensions, it is often advantageous to use a Cartesian vector analysis when applying the equation of equilibrium. To do this, first express each known and unknown forces and couple moments shown on the free body diagram as an Cartesian vector. Then set the force summation equal to 0. Take moments about a point O that lies on the line of action of as many unknown force components as possible. From point O, direct position vector to each force, then use the cross product to determine the moment of each force. Here you can see the origin is in the middle, and we have to draw out the direction of the force and also the moment of the force. The six scalar equations of equilibrium are established by setting the respective I, J, and K components of this force and moment summations equal to 0. If a body is supported by a minimum number of constraints to ensure equilibrium, then it is statically determinate. If it has more constraints than required, then it is statically interminated. To properly constrain the body, the reaction must not all be parallel to one another or concurrent. So we have come to the friction. Frictional force exists between two rough surfaces of contact. These forces act on a body so as to oppose its motion or tendency of motion. So we can see here the frictional force is opposite of the motion of the object. A static frictional force approaches a maximum value of F equals to mu n, where mu is the coefficient of static friction. In this case, motion between the contacting surface is impending. Here, this is the impending motion. So the frictional force is opposite of its motion. If slipping occurs, then the friction force remains essentially constant and equal to Fk equals to mu k, and here mu is the coefficient of kinetic friction. So when the object is moving, the force also opposite of it, and the mu is become the coefficient of kinetic friction. The solution of a problem involving friction requires first drawing the free body diagram of body. If the unknowns cannot be determined strictly from the equation of equilibrium and the possibility of slipping occurs, then the friction equation should be applied at the appropriate points of contact in order to complete the solution. It may also be possible for slender objects like crates to tip over, and this situation should also be investigated. This is some example for the frictional force happen. These are some example which frictional force act on it. Wedges are inclined planes used to increase the application of a force. The two force equilibrium equations are used to relate the forces acting on a wedge. An applied force P must push on the wedge to move it to the right. If the coefficient of friction between the surfaces are large enough, then P can be removed, and the wedge will be self-locking and remain in place. Screw. Square-threaded screws are used to move heavy load. They represent an inclined plane wrapped around a cylinder. The moment needed to turn a screw depends upon the coefficient of friction and the screw lead angle theta. If the coefficient of friction between the surface is large enough, then the screw will support the load without tending to turn. It will be self-locking. And these are the equations for the screw motion. Flat belts. The force needed to move a flat belt over a rough curved surface depends only on the angle of belt contact, beta, and the coefficient of friction. And here it shows T2 is larger than T1 and T2 is equal to T1 exponent mu beta. These are three more examples: collar bearings and discs. The frictional analysis of a collar bearing or disc requires looking at a differential element of the contact area. The normal force acting on this element is determined from force equilibrium around the shaft, and the moment needed to turn the shaft at a constant rate is determined from moment equilibrium about the shaft axis. If the pressure on the surface of a collar bearing is uniform, then integration gives the result shown. Here is the here is the formula for the frictional force calculation. And the journal bearing, when a moment is applied to a shaft, is in a non-lubricated or partially lubricated journal bearing, the shaft will tend to roll out and the side of the bearing until slipping occurs. This defines the radius of a friction circle, and from it, the moment needed to turn the shaft can be determined. The moment is equal to RR sine theta. Rolling resistance. The resistance of a wheel to rolling over a surface is caused by localized deformation of the two materials in contact. This causes the resultant normal force acting on the rolling body to be inclined so that it provides a component that acts in the opposite direction of the applied force P causing the motion. This effect is characterized using the coefficient of rolling resistance A, which is determined from the experiment. And that's all from me. Thank you.